thought.
Absolutely. Thank you so much for reminding me. Yep. Okay. So as we said, so video tracking is pretty simple. Basically, you have video, you have done some object detection in the first slide or the first frame of that video, and you're trying to follow like the tracking of those objects, right? So for example, you have cars on the highway, you're trying to count how many cars are there. You would like to have a certain algorithm that allows you to basically track the cars that are like moving through the image, such that you don't count them twice, right? So when a new car comes in, you increase, for example, a counter, and you tell the traffic people how many cars are coming into the city and going outside of the city. And in order to do that in a good way, you would like not to recount the car every new frame, right? So every new frame that you receive, oh, this car, I've seen it again, but I will increase the counter another time just for the sake of it. So that's not something that we would like to do. What we would like to do is you see a new car coming into the video, you count it the first time, and while it is moving inside your video, so while it's like traversing the road, let's draw it here like this, right? So let's imagine this is the road. The car arrives here. The second that you see it, you increase your counter. And while the car is moving, the camera, for example, is in here. Here's the camera. It sees this. While the car is moving, you're not going to be counting it again when it reaches here. You're not going to be counting it again when it reaches here. So you're going to be counting it only once and then tracking it through the road. This will help you basically build better, classifiers or, counters. Another technique might be to just put a line here, and any object center that passes through this line, we'll just count it. So we don't start the counting the second we see it. We start the counting when it passes. But these are like different techniques. And for today, we will see how we can do that task using object or video tracking or object tracking in videos. Now, the good thing about videos is they are in sequences, right? So as we said, the car starts here. The next frame, you already know the same car is not going to be, for example, here, right? It's going to be very close to it. Here's the next frame. And the next frame. And this is the next frame. And the next frame. So in the majority of tasks, or in the majority of cases, in a video, the object that you're interested in, here it is, in the next frame of that video, it really shouldn't be too far from its initial location. So each frame, this is frame 1. On frame 2, it should be a little bit to the right, a little bit to the left, a little bit to the top, a little bit to the bottom, but it should not be completely different location, especially if your camera is stationary, right? So if your camera is on the same place, it does not move, and only the objects are moving, that simplifies your task a lot than, or your expectations for the object tracking. So that said, what we're trying to do right now is we will try to leverage the fact that the video or the objects in the video sequence to sequence or frame to frame are always very close to each other, or that's what we expect. Of course, there are some exceptions to that rule, and sadly, all of our video tracking techniques that we will be talking about today will not work for these exceptions, right? So our video tracking techniques that we will be seeing today, and majority of what you will be using, for example, during the lab, or if you go to a company and you are using a different algorithm, a little bit more advanced, it's still gonna fail for that specific case, where, for example, the object is here, and then the camera just moves very, very sharply, and then comes back to that same object. For you, it's going to be a new human being, right? Unless you do some sort of facial recognition, that might help a little bit to the object tracking. So as we said, there are two techniques to do right now the video tracking or the object tracking, either by recognition, right? Each object, you will recognize that specific instance of the object. So for example, if you have a phone, this is the iPhone, right? And you have another phone, which is, let's say, Samsung. So you could do like a video tracking, and another like on top of it, every time, every frame, you will be detecting first the phones, And then you will be doing some recognition based on, the photo itself. If the initial or the first iPhone had a certain crack, then you will be trying to look for that crack to, track that object on every frame to make sure that you have the same iPhone again and again in each frame. But this is quite difficult to do if it's not for human beings, right? So human beings, it's easy because our faces are different, or we would like that our faces are different. Whereas for things that are like manufactured, as we just said, an iPhone, all iPhones look the same, especially if it's the same, model, same color, same everything, then you will have at least like 1,000 iPhone of the same exact dimensions and shapes. The other approach would be to build a video tracking technique based on, the current frame, the next frame, and as we said, the hope or the hypothesis that individual objects in that frame or in that video should not be moving drastically from one position to the next in sequential frames. So again, this lecture, by the way, is completely done by Professor Fahim, and it's a very good lecture. So this is why we will be reusing it for our lecture today. Sorry. The contents of the lecture, we will be speaking a little bit about is object tracking models, the components of an object tracking algorithm. We will see a little bit about online object tracking and offline object tracking, and then we will speak about the common problems of object tracking. I think we've covered a little bit some of those common problems already today by speaking about, like cameras that are moving, so non-stationary cameras and stuff like that. Or objects that are too similar, or objects that are too, crowded. So it's just like everybody is in the same place. So for example, you could imagine Times Square at like the peak of its, where lots of people are there. You're obviously not going to be able to track every human being's direction or every human being, going in which direction. That's a very difficult task unless you're China. So object tracking is, as we discussed, the goal of object tracking is to keep track of an object in a video sequence. It's a very simple goal, and we will see different techniques to do that. Object tracking is an old and hard problem for computer vision because there are lots of objects, as we said, per frame. And the problem is sometimes the frames, sometimes they're moving, sometimes they're not moving. Sometimes the camera is moving, sometimes the objects are moving super fast. So for example, I don't know, you would imagine like a rocket, so it just passes through your video or your frame very quickly. And sometimes they don't, sometimes they move very slow. Let's say you are watching, I don't know, animals in the wild, and it's a turtle, and they're pretty slow, right? There are various techniques and algorithms which can try to solve this problem, and some of them are motion-based, and the ones that we actually care about today's lecture are the visual appearance-based. So the motion-based algorithms, we will start with those because we'll just like quickly go through them because we're not going to describe them in more detail. But motion-based algorithm or model is developed in which hopefully to capture the dynamics or the dynamic behavior of an object. So it's not going to be learning actually the object. It's not going to be like looking at the object saying that this is, for example, this is Ahmed, this is Imad, this is something else. So it's not going to be it's not going to be doing any recognition or, deep learning stuff that will, understand the object itself. It's just going to look at the video and try to predict what's happening, what's moving, what's dynamically changing in that video. It predicts the potential position of objects in future frames. The drawback is the motion model can fail in scenarios where motion is caused by things that are not in a video, or abrupt directions or speed changes. These algorithms will be, the most, or the two common that that I worked with are optical flow and Kalman filtering. Optical flow is it's pretty much still used till today, especially if you're, working on videos and stuff like that. So basically video detection or video classification or stuff like that. What happens is optical flow allows you to understand what is moving inside an image, or inside a video. So for example, if you put a camera here, let's say, again, this is your camera, right? It sees this. and this is the road. It will basically do some calculations, and here you will be able to see what's only the parts that are changing. So it kind of like masks everything that is not changing, and it will show you the car while it traverses through the image. So it will be like everything is black, but the things that are moving or the things that are changing will be, shown as changing objects in here. So this is what optical flow does, and it's a very useful information if you are, as we said, working with videos, trying to do some classification and stuff like that. Another technique is Kalman filtering. Kalman filtering is a very beautiful model. According to what I've heard, you've already done it in another course, but it's a very good algorithm. It's basically still now used for things like NASA's rockets or things like self-driving cars to help them understand basically evaluate better their positions or their speed, right? Which is pretty cool. I think it's a very nice algorithm that allows you to like estimate a specific hidden information that you would like to either validate because you don't have accurate sensors, or you would like to just predict because you just have no idea on how to calculate it in another way. But it's pretty cool. Now, the other type of models that we will be discussing today, which are like the ones that we will go too much in depth with, are the visual appearance based models, or VAMs. So VAM tries to understand the appearance of the object. So they try to do some deep understanding or deep learning of these objects. Technically, they learn this to discriminate the object from the background. Visual models can be either single object trackers or multiple object trackers. So you can imagine single object trackers are much easier, and going from single object tracker to multiple object tracker shouldn't be that extremely difficult. So single object tracking, for example, here you have football and you're tracking it across the field, right? So this is easy because there's only one football on stage. And if there are two, then the game is paused until the second one is taken out. So that's a much easier task. Whereas for multiple object tracking, it's a very difficult task, right? True. Usually when players are wearing different clothes, so that simplifies, or different colors, that simplifies a little bit the thing, especially when they are like turning and on corners where they will be all mushed almost into the same location in the frame. But if they are all wearing different clothes and they are a little bit distinguishable, you can still be able to do it. So even as a human being, it will be difficult for you to track all of these objects if they were all wearing the same thing, right? So same thing, for example, for football. If you're watching football and you're trying to track the players, sometimes you make like a mistake. Oh, this is, I don't know, someone else, and this is Messi, but it's not. It was Iniesta. So if they are wearing the same things and you are looking from afar, it becomes even a harder task. So this is why multiple object tracking is a little bit more difficult than just single object tracking. For the components of a visual-based object tracking method, the algorithm really take four main components. The first one is the target initialization. The first step is this one, target initialization, where we need to basically define the initial state of the target by drawing a bounding box around it. So as we said, the first frame, what you will be doing is you will do your object detection on that first frame. Once that is done, sorry. So the idea is basically to, as we said, draw the bounding box of the object or the target in the initial frame of the video, and the tracker has to estimate the target's position in the remaining frames in the video. So this will hopefully help you reduce basically your calculations. There are different techniques right now which do this. So for example, instead of only doing the object detection in the first frame, they kind of do object detection every time that they feel there is a major change between two frames, right? So instead of doing it on all the frames or doing it only on one frame, they have a learning algorithm that just tells them, oh, right now you should use the full object detection model right now. And so for example, every 10 seconds, you have to do this drawing the bounding box from scratch. But these are like just different variations, and it's much simpler. But majority of these algorithms, they only do this initial state or initialization on the first frame, and they don't have to repeat it again multiple times. And if they do, they try to do it as low as possible, you know, as non-repetitively as possible. The second part is the appearance modeling, right? So now we need to learn the visual appearance of the object using some learning techniques. Hopefully it's going to be through deep learning, right? In this phase, we have to model and learn about the visual features of the objects while in motion, various viewpoints, scale, illuminations, and etc. So for example, you're watching a ballet dancer, and they just like turn a lot, right? So you will be seeing all, so right now you're looking at their face, tomorrow you're like, next slide, they're like, they turn super fast, right? So the next frame, you're already looking at their back. In the next frame, you're looking at something else. They go to the shoes or something like that, right? So it's a very difficult task, because, you know, the objects are in motion. They are doing extremely challenging, you know, positions. Sometimes they're jumping, sometimes they're just running. They do a lot of stuff, right? Different illuminations as you make, so in the same example also. So for example, you're watching some of these, you know, sports where the player is just moving a lot and moving extremely fast. And sometimes they just like throw it a little bit dark. Sometimes it's a little bit, you know, it's fully illuminated. Sometimes it's all dark, but the object itself is illuminated, focused completely. So it's different types of illuminations, different scales. Sometimes they zoom in, sometimes they zoom out. So it's a very difficult task to do this well and fast, right? To do this well for each frame, and to do it fast, because, you know, you're going to be doing it for each frame. Motion estimation is basically the third one. So the objective of motion estimation is to learn to predict a zone where the target is most likely to be present in the subsequent frames. So as we said, the whole reason why we are able to do this object tracking in a simpler manner, right, other than, you know, fully doing facial recognition or something like that, it's because we already know that the objects, they're not going to go into like a completely different position, sequence into sequence, right? So from this sequence or from this frame into the next frame, we don't expect a drastic change in the position of that object. Whereas, for example, here, this is what we're trying to do. We're trying to predict the zone where that target might be for all the subsequent frames. So for example, if in our case, we have like a road, right? And in the majority of the roads, here it is, here's the camera. A car starts here. You can already predict that they have just one way, right? They're just going like this. You already know where they are going. They're not going to go to the other side. They're not going to go like to the left. They're not going to go to, I don't know, this is, for example, a field. Here are some cows. They're not going to go kill the cows, right? Or the majority of the drivers are not going to do that, right? So you already know, you have like an expectation of where that same object will be going to next. And that helps you basically reduce the search party for that one. So you're not really searching all over the image. You're like searching in specific locations. And the final part would be the target positioning. And this one is basically you have a search place and you just lock it down. So motion estimation gives us the possible region where the target could be present. And we scan that using the visual model to lock down the exact location of the target. So this one gives you like all the possible places where he will be in all the possible frames in the future. Whereas this one just gives you exactly where it is right now. Generally, tracking algorithms don't try to learn all variations of the object. So for example, I don't know, like you're not going to be learning things. So for example, here, and as we said, there's the road. The thing that you will be learning to track these, you know, objects in this frame are not the same. For example, here we are like working on cars, right? They're not going to be using or as difficult as tracking, for example, those Formula One cars, for example, in very difficult roads. So this task is much more different than this task. And each tracking algorithm or each tracking, variation will be focused kind of to its own scenario. So it will be kind of, well, let's say simplified to its own scenario. It's only the variations that they are seeing in that specific case. And the first type of algorithms that we will be seeing is the online training trackers. So these are both algorithms that we'll be seeing today are CNN based. One of them will be online and the other one will be offline. And this online method is called multi-domain network, or MDNet. The multi-domain side comes from basically the first, let's just go to it. Comes exactly from the first step of the training of this algorithm, and we will see that in detail right now. Right.
Excuse me, Professor.
Yep.
I have a question, but I'm not sure it's like a good or but maybe a silly question. Like in one frame, our like object is on the upper corner, and in the next frame, it will be going to the in the down bottom corner. So at that condition, our model work very well or not?
No, that's what we're like saying, that it should be impossible for such major changes to happen. So for example, here you have Usain Bolt, he was here.
Mm-hmm.
The next frame in literally like 0.05 seconds, right? So it's a very, like the very next frame. It's a very small period of time, right? It's a very small period. You don't expect Usain Bolt for in like 0.05 seconds to go from this place to this place, right? He's a human, right? So he will go from here to here. You get what I'm saying?
Yes,
so this
yes, I understand.
This is absolutely like the only criteria that we have to apply these object tracking techniques, right? It's that changes in subsequent frames should not be, or especially in sequential frames, should not be extremely drastic, right? So it's not something that appears here and then appears here and then appears here. So if you are watching, for example, an anime and the characters, they are very good and they just jump from one place to the other, then in these cases, video tracking is not your friend, but facial recognition is, right? So for example, each individual character usually has their own, colors and their own, clothes and face and stuff. So you can easily recognize that that's right. So here you had the first character in here. They disappeared for some reason, and now they're no longer in this place, and they just appeared again instantly in this location. In this scenario, you're not going to be doing object tracking. You're going to be doing, as we said, facial recognition or object recognition, right? So you will be recognizing each individual character by hand. And you say that here, I recognize that this was Naruto or something like that. And he appeared again in this location. And this is Naruto again. So it's not kind of tracking. It's fully based on object recognition in that case. So if you have major jumps from one slide to another or from one frame to the next, do not use object tracking. Definitely use something like recognition, right? But that's a very good question. Thank you so much for asking. Yep. The motivation for let's go back to our MDNet, right, which is a multi-domain network. The motivation for it have like three problems. The first one is the pre-training problem. They would like to solve this pre-training problem. They would like to do it like in a multi-domain setup. So it should be something that is easily fine-tunable to multiple types of objects or multiple types of settings. And the network size problem, we will see exactly what that is. So the pre-training problem is to pre-train a CNN for large-scale feature extraction on large-scale data, which is not reasonable for all types of, every time you're going to be doing object detection or object tracking, you're going to be doing this pre-training. So preferably a realistic approach would be to train the CNN on the tracking model directly on the video of tracking data. So hopefully what will happen here, you will have your layers already pre-trained, for example, on VGG network, and then you just fine-tune them on your own tracking data, right? So your CNN because this is a CNN-based algorithm, right? Your CNN is already pre-trained, the convolutional layers are already pre-trained on, for example, let's say a different task, which is just classification. They're not being trained for, video tracking. You don't train each, CNN on video tracking per se, but you do pre-train it on image classification. Then you bring it here, and when you are training it for video tracking only on like a small data set of just one video or a couple of videos that are related to that scenario. For tracking targets, their types may be different, but there should be some commonalities, including edge gradients, etc., which require learning or network learning. So basically that first few convolutional layers should be the same for the majority of the object tracking techniques. As you have already seen in this course, like the first few weeks, we have seen what convolutions are, right? We have seen that convolutions are just a way, or a very powerful way, to detect edges, to detect gradients, to detect corners, or to detect many different types. And of course, those detections were just like hard coded coefficients for the convolution, whereas a convolution that is learning from scratch will be able to learn even better, right? So it's doing even more than just finding edge gradients and stuff like that. It's definitely doing something that we do not find as humanly interpretable, but definitely it is at least as good as basic edge detection or stuff like that. The multi-domain problem is kind of back into the pre-training problem. It is more difficult to train CNN directly with tracking data. Why? One object is the target of the video, whereas the other time, or another video, it could be just another background character, right? So let's imagine this one, right? Let's say you are in Innopolis and you are inside the university trying to track the students. Very nice. Now you go outside. You are in front of the university. Sorry. You are in front of the university right now. So this is the university, let's say, and this is the roundabout in front of the university. And now you have a camera here trying to track basically the cars. In the first scenario, humans were the interest of your model, right? You were tracking humans inside the university. In the second scenario, you are tracking cars, right? Outside the university. Hence, these humans that will be walking on the street are something that is completely ignorable for you in the second scenario, whereas in the first scenario, they are the absolutely target of the video, right? So this is the problem. Basically, you have one object is the target of the video, whereas in another one, it should be just another background character that we do not care about. Additional challenges, there is a lot of background clutter, occlusions, illumination variations, and so on. The network side problem, basically the CNN network in detection, so object detection or classification or segmentation, is very large. So probably we have, right now, at least with YOLO V8, the smallest version, it's not that big, but it still is very big, right? So it's not going to be something that gives you absolute, what is it called? Real-time detections on, CPUs or something like that. However, in tracking, the label is pretty simple. It only has two categories. Are you my target or are you a background, right? Are you my target character that I'm trying to look for example, let's say Naruto, or are you just a background? Are you a leaf or a building, something like that, right? I don't care about you. So what they do is with the MDNet architecture is they will first start with these shared layers. These are pre-trained layers. Here we go. So these are just basic CNNs, right? So you have a couple of convolutional layers and a couple of fully connected layers. Two fully connected layers. These are coming from the VGG network. VGG is a network provided, I think, by Google. Let me just confirm. VGG network is one of the most commonly, how do we say this? Commonly used deep learning computer vision models, especially for things like style transfer. For some reason, they really love it. VGG stands for Visual Geometry Group, and it is just a basic CNN that is pre-trained, if I'm not mistaken, by Google, and it gives very good results. Yeah, VGGNet. Let me check who did it. Okay, PDF. University of Oxford. Absolutely not Google. Yeah. So by the University of Oxford, definitely better than nothing. Yeah, let's come back. Yeah, so the first few layers, as we said, are just basic VGG network, pre-trained already, and we're not going to be worrying that much about the shapes or stuff like that, except that the feature maps sizes are adjusted by input size. So for example, if it's a very gigantic image, it should have like a bigger version. Basically in here, as you can see, a little bit, if you can see it, this scenario, we have a human being walking from this edge of the room till the final edge of the room. This other scenario, we have a car walking from this side to all the way up. This scenario, we have a human walking like a biker. Yeah, this is a biker walking, I think, or biking across a train rail. He's gonna die. But yeah, so as you can see in here, we have this fully connected layer number 6. So it's the 6th layer of the model. So it's a very small model, first of all, right? So we have three convolutions, 2 shared fully convolutional layers, fully connected layers, 4 and 5. And this one is just another fully connected layer number 6. We repeat it multiple times. So for example, here, this is the first scenario. Here, this is the second scenario. And here is the kth scenario. We have multiple scenarios. Each one of these scenarios will be treated as a different domain. And each one of these layers, FC6, 2, FC6, 1, FC6K, will be trained for a domain-specific loss or a domain-specific task. So our CNN is trained by the stochastic gradient descent method, where each domain is handled exclusively in each iteration. So they will first start with this video, train only this part. Then they will go to this one, train only this part. Then they will go to the next, train only this part. And when they finish, they go all the way back and train this part, and again, and again, and again. Where each domain will be handled exclusively in each iteration. In the kth iteration, the network is updated based on a mini batch that consists of training samples from the kth mod k. So mod just means division and the rest of the division. And that allows you to have this cyclic training, right? So you start with this one, next. When you finish, you go back to the first one and you get next. That's why they use this mod in here. Sequence, where only a single branch, well, basically the corresponding branch, is enabled and is being trained. It is repeated and the network is converged, or the predefined number of iterations is reached. Through this learning procedure, the domain-independent information is modeled in the shared layers from which useful information or useful generic feature representation are being updated. So basically, this part of the network will be trained, hopefully, in a domain-independent manner. Since it is being trained for all these different domains, it should be generalizable or generic enough to generalize to any other domain. That's not always the case, but that's the assumption that they are making, right? Training on multiple domains leads to domain independence. Some other training details, they're very basic here. This is how many training iterations. The learning rate for the convolutional layers is 0.001. Learning rate for fully connected layers is 0.01. This is the momentum, and this is the weight decay. Momentum and weight decay are just parameters for different learning algorithms or different optimizers, basically. Now let's go to the tracking part of MDNet, right? So we've seen how they train the first part of the model, right? So they've seen how they train this multi-domain network or domain-independent network. Now let's go to the actual domain-dependent part, right? So let's see the tracking part on a specific example. Right. So what they do is, after the completion of the training, what they do is just they throw away everything that is, all of this, because we're not going to be training as we said, a tracker for this setup and the tracker for this one and for this one at the same time. We're going to be training one specific model at a time. So here we have these layers. These are the shared layers up till fully connected 5. The fully connected 6s, as we have seen before, are just domain specific. And now instead of having like 100 or K different FC6 or fully connected layers number 6, we have just one for our specific task, right? Fine-tune basically the new domain specific layer and the fully connected layers in the shared network online at the same time. So basically this, and that will be trained. These parts, which are a little bit more difficult to train, will just be frozen completely. So the tracking procedure is explained as tracking control and network update, hard mini-batch mining. So we will be speaking a little bit about hard mini-batch mining right now, but we will jump to it again in the end of the lecture because it just requires a little bit more thinking. Bounding box regression, right? So these are the 3 steps. The first step, as we said, is tracking, control, and network update. Author considered 2 complementary aspects in the visual tracking. The first one is robustness. The second one is adaptiveness, by doing one as long-term updates, and the second one is short-term updates. The long-term updates used are performed in regular intervals using positive samples collected for a long period. We will see this in an image. It will be much clearer, but let's go back. Whereas these short-term updates are conducted whenever potential tracking failures are detected, where basically when the positive score of the estimated target is less than 0.5. So in this case, you have, for example, your object, the actual place is not being detected correctly from one frame to the next, right? So it's a very short-term tracking failure. This is what we're trying to track. We're trying to track long-term correct tracking, and short-term potential failures. We're trying to find those so that we have them, and then we train on them more. And this is also related to the hard mini-batch mining setup, right? We will go there, right? So the long-term and short-term updates. To estimate the target state in each frame, n target candidates x1 till xn are sampled around the previous target state, are evaluated using the network, and we obtain their positiveness score, f positive of xi, and negative scores f negative xi from the network. So as you remember, the network has 2 outputs. The first output is basically the object, the positiveness score, and the second is the negativeness score. So negative means it's background, and positive means it's the target. So yeah, so here we have, as we said, for each one of these different candidates, we have different positiveness scores and different negativeness scores, and we will basically take the optimal as just the one with the highest positiveness score. So just like, for example, you have multi-class classification, and your class is basically the class with the highest probability. It's kind of similar in here, but we don't have the softmax, right? Also related to that same concept is the hard mini-batch mining. The majority of negative samples are typically trivial or redundant, right? So for example, here's your object, here's the image. If you keep on sampling, for example, this as negative samples that are used to train your model, these are useless. The model already knows that the object is not here. The object is here. The next frame is probably going to be in here. So keeping or repeating these negative samples, which are like extremely far from the object and extremely useless and trivial and clear that they are not part of the object, is not going to help the neural network train any better. So in detecting by detecting approach or tracking by detection approaches, while only a few negative samples are effective to the training. So usually they are the ones that are actually close to the object. Hence, the ordinary stochastic gradient method, where the training samples evenly contribute to the learning, easily suffers from a drift problem since the negative samples are considered insufficiently. The solution is called hard negative mining. hard negative mining. So we're basically going to be selecting these negative samples, specifically the ones which are hard for the model, meaning based on like the previous iteration of the training, if the model makes a mistake, that's what we will be sampling as the negative candidate for the model. So the negative sample for the training, right? So we look back any issues that the model has done in this iteration, we save it, we use it to train the model on the next iteration. So here, for example, this is the first mini batch of what are they called? Negative mining. And as you can see, it's all across the world, like it's everywhere around the image. We've seen how the model is being trained a little bit, and now the model is more certain about its results. So the negative samples are now being, more or less condensed in this area. After 30th approaches, the model is now being very, very much certain and does not make issues or errors in this region. It makes only errors in these regions. And this is why now we're sampling from a more condensed area. Same thing, for example, in here, you see in the start, we're trying to sample negative images or negative frames from all around the image, but as learning improves, we're now sampling only the places that the object is making or the classifier is predicting wrongly, right? So only the issues of the classification are used for negative sampling. And then the final part is just the basic bounding box regression, where we've already seen that. It's just basically, let's go through it, right? So due to the high level of abstraction of CNN-based features and data augmentation strategies, which samples multiple positive examples around the target, MDNets sometimes fails, and to find basically the tight bounding boxes enclosing the target. They apply the bounding box regression technique, which is very popular in object detection to improve target localization and accuracy. So this is very similar to, if you remember, when we were speaking about things like, let's not go to YOLO, but let's go to faster RCNN, for example, where in the first part, you are trying to do the region proposal network. And in the region proposal network, you already have some anchor of a specific shape, right? So the anchor already has a good shape that, let's say like this, the object is here. So it's not bad, right? So it's not bad, but we do improve it using the second step, which is basically the bounding box regression, which is part of the RPN, right? So the bounding box regression, it just predicts, as we said, the X, Y, width, height, displacements of this anchor, and it just tells you how to change the anchor basically to perfectly fit your model. So this is what bounding box regression does. It just tries to predict the the different locations or the different coordinate changes that would fit that object perfectly. Given, so this is just like a little bit more explanation. Given the first frame of a test sequence, we train a simple linear regression model, so it's very fast, to predict the precise target location using convolutional 3 features. Oh, this one. The last convolutional feature, or the last convolutional layer. Let's go back. Of the sample near the target location, in the subsequent frames, we adjust the target location estimated from equation 1 using the regression model if the estimated targets are reliable, i.e., if the the positiveness score for, or the most optimal positiveness score of any candidate is above 0.5. The bounding box regressor is trained only in the first frame, since it is time consuming for online updates, and incremental learning of the regression model may not be very helpful considering its risk. Refer to this for more details about the use of the same formulation and parameters. It's just basically a very simple technique that is basically a direct linear regression, takes whatever candidate you think is the most optimal and gives you the even more optimal location of that object. So although we might take a break here, but I would like to actually take the break at the end, so we have enough time to discuss a little bit about your the final exam and your project. So let's just continue, and if you need any break to like relax or to think a little bit, get some coffee, you can just ask me a bit later on. So now we go to the offline based tracking. So offline tracking is a bit easier because you now have a lot more flexibility in training, right? So you're not pressured during your training to reduce basically the training time as much, because now you have all the time in the world, you have all the data in the world, you have everything you want. And the name of the algorithm that we'll be using is generic object tracking using regression networks. They are very similar, as we've already seen. Everybody uses regression networks, but now we'll see the slight differences, right? So GoTurn here applied the discriminative power of convolutional neural networks to the task of visual object tracking. It is offline learning tracker. It's offline learning tracker based on CNN. The tracker is trained using thousands of videos. So now we have a lot more access to videos, right? So it's not like the online approach where you have access to a few set of videos, or just one in most cases, right? For general object tracking, this tracker can be used to track most of the objects without any problem, even if those that were not at all part of the training set. So even for the objects that were never used to train it, it can start learning how to track them if you tell them this is the object. So you tell it this is like a white cat. It has never seen a white cat before, but it's still able to track any white cat in any video. GoTurn also can run very, very fast. So it's much slower during the training, but in the actual life, it's very, very fast, meaning with 100 frames per second, which is way above the threshold that we want for, doing, what is it called? Real-time detection, right? So for real-time detection, we're aiming for something like 13 or 11 to 13 frames per second. And if you want to go like even crazier, you could go to like 24. Anything above 24, you're just like wasting your calculations. So as we said, during the training, you take hundreds and hundreds of training videos or images with sequences, and you just send them through the neural network that will be learning some generic object tracking algorithm. So at a high level, what we'll be doing is we will feed different frames of a video into the neural network. The network successively outputs the location of the tracked object in each frame, and then we train the tracker entirely offline with videos and with video sequences and images. Offline training procedure basically learns a generic relationship between appearance and motion that can be used or can be generalized to track novel objects at test time with no online training required, right? So this one does not need to be fine-tuned for the specific use case that you have, mainly because it's being trained on a very large amount of data beforehand. So here, for example, we have the current frame. This is the search region of that current frame. It goes here, we have everything that we want. And sorry, this is the previous frame. This is what we're trying to track. This is what we want to track. We tell it this is what we want to track. And basically it goes through the network. And then here, this is the current frame. Now you are doing your actual job of tracking. This is the next frame, right? And in the next frame, we will try to find a search region. And then in that search region, we will try to even like make the location even more fine-tuned by predicting the exact location of the target within the search region, right? This is the search region. It's very similar to the previous location of the object. And then we try to find the perfect prediction or the perfect location of the object. The layers are simply the first 5 layers of the CafeNet, which is another architecture that is based on Caffe, I think, which is just similar to TensorFlow and stuff like that, but it was trained by, I think, a few mathematicians and like a very famous neural network researcher. I forgot his name, but it's a good network. Not the best, but it's a good one. The outputs of these convolutional layers are concatenated into a single vector of length 4096. And the last fully connected layer is finally connected to the output layer that contains 4 nodes representing the top, bottom, and basically left and right, or basically this, or as we said, if you want to do it with this point, like X and Y, and this point, X and Y. During the testing, now you are using an object that probably you have not seen before, right? So this type of object you have not seen before. You have the previous frame, goes to the neural network. It is frozen because you're not doing any training. You have the current frame, and it basically can tell you where the actual object is inside the current frame without any training, right? So we're saying that it does that without any training. The network hyperparameters are taken as defaults from the CafeNet, and for each fully connected layer, they're using some dropout and ReLU for non-linearities. Dropout is a very simple technique. I'm sure you are familiar with it. Basically, some of the activations of that specific layer will be just turned off, will not go, will be just 0. And this kind of forces the neural network to learn different paths of the same information. That might look like it's a redundant thing, but that's very good for, reducing overfitting, or like forcing the different nodes to, pick up the slack from the others, right? So make better decisions even in situations where you don't have enough information. And of course, ReLU, you're all familiar with that, right? The training and loss functions. The loss functions will be L1 loss function, just as we have seen, and any bounding box regressor for YOLO or bounding box regressor for faster RCNN, all of them, they are using the L1 loss to basically predict the perfect bounding boxes. And the L1 loss is very similar to the L2 loss, but instead, we're already familiar with that, right? So instead of using the L2 loss squared, here you're just using the absolute difference, and that's it. That's the only difference, right? Of course, there are differences in the actual results. Why are you using this one versus the other one? And I'm sure Professor Khan has given you the whole discussion about this shape of the loss function versus this shape of the loss function and the interaction between the loss function and the optimizer, right? Input/output format. So what we're trying to track, or what to track in case there are multiple objects in the video. So this one is a little bit more difficult, as you might imagine. The network must receive some information about which object in the video is being tracked. So here it's easy because, well, there's only one object. If there are multiple objects and you're trying to track a specific one, you must tell it which one is being tracked. To achieve this, input an image of the target object into the network. So you just input basically an image of the target object into the network. In the cases where, of course, these objects are highly occluded or overlapped, or how to say this, like crowded, right? It's just not going to work. That's just not going to work, not ever, right? The network will track whatever object is being used as input in this crop, and this input allows the network to track novel objects that have not seen before, that it has not been seen before. Where to look? To find the target object in the current frame, the tracker should know where the object was previously located. Since objects tend to move slowly or smoothly through the space, as we said, there is no jumping from the top left corner to the bottom right corner in one frame. This is extremely difficult to manage, and if that's the case for you, then you should switch into object recognition instead of object tracking. Since, as we said, objects tend to move smoothly through the space, and the previous location of the object will provide a very good guess of where the next step, like the next place will be, or the next location of that same object will be in the next frame of where the network should expect the currently find the object. It is achieved by choosing a search region in a current frame based on the object's previous location. The network's output, the goal of the network is then to regress the location of the target object within the search region. The network outputs the coordinates of the object in the current frame relative to the search region. The network's output consists of coordinates, the top left and bottom right corners of the bounding box. Again, there's no difference between the top left and bottom right corners or just X, Y, width and height. They both represent the same thing. Very important thing to note is they are always relative. Let me check. Yeah, relative coordinates to the search region. So it's not absolute coordinates, they are relative coordinates. Applications, you can apply this in hundreds of situations, for example, surveillance, human-computer interaction, medical imaging, traffic flow monitoring. So for example, you're monitoring, I don't know, you put some device into the human being and you're trying to follow the path of that, or you're trying to follow, you know, the progress of cancer or something like that. Traffic flow monitoring, as we said, you just calculate the number of cars that are going into the city and the number of cars going outside so that, you know, traffic people can have better systems, and human activity recognition, and etc., etc., etc. There are, as we said, tons of common problems that that we will be facing. Tracking an object on a straight road or a clear area might sound very easy, but hardly any real-world application is that straightforward or that easy, right? So as we said, like this, you have the camera and you have the road. Here's the car. Just one car comes in, goes, yay. Another car comes in and goes. So it's an easy situation that we've just described, but in real life, things are not as easy, right? So as we see in here, for example, occlusion, right? So this third object was being monitored in the start, but then it just completely disappears because it was being occluded by these two people. And that's something that happens all the time. Variations in viewpoints also is a very difficult task. How can you recognize that this person is the same one as this from different points of view? Common problems, non-stationary camera. This is even worse. This is the worst situation that could happen to you. When the camera used for tracking a particular object is also in motion with respect to the object, it can often lead to unintended consequences. A robust tracker for this problem can be very helpful in important applications like object tracking for drones and autonomous navigation. Even drones, they don't walk that fast like this, but if they like turn around or they change completely the direction of the camera, then usually that speed of change is very, very hard for any object tracker. Other common problems, scale changes, background clutters, as we said, illumination variations, low resolution, and annotating the training data, which is a very, very annoying task, right? You've already done the, yeah, for example, your task for the bonus points or the bonus task was to annotate a training data set for segmentation, and you've already seen how that is very hard. Try doing the same thing for videos, it's even worse, right? If you're interested to do some research or some reading, these are some good slides. Before I say thank you, let's just go back to hard negative mining, as we said. Let's say I give you a bunch of images that contain one or more people, and I give you bounding boxes for each one. Your classifier will need both positive training examples of a person and negative training examples of not a person. For each person, you create a positive training example by looking inside that bounding box. Here's the person. And we generate some, samples that are positively inside it. Anything that is outside is just generated randomly, and it happens to fall outside. So anything that is outside will be considered as a negative. But how do you create useful negative examples, right? Not just any negative examples, but useful ones. A good way to start to generate a bunch of random is to start by generating a bunch of random boxes. And for each box that doesn't overlap with the positive, we consider it as a negative. That's generating a negative. How can we make it useful? So you have the positives and negatives, and you train your classifier and test it out. You run it on your training images again and again with the sliding window, but it turns out that your classifier isn't very good. So your classifier is making some mistakes because it throws a bunch of false positives. meaning these are negative samples being predicted as false. And these are the samples that you should focus on. So people detected where there aren't actually any people. So these are actually false or negative samples. Let's say negative samples. Yeah, these are negative samples that the model is wrongly predicting. So if you want to train a better classifier, you could already use these negative samples as the negative samples of the next step. A hard negative is when you take that falsely detected batch and explicitly create a negative example out of that batch and add that negative to your training set. When you retrain the classifier for the next iteration, it should perform better with this extra knowledge and may not make as many false positives. So this is mainly it for today's lecture. As we said, it's a very quick lecture and it's quite simple. But yeah, so I would like to discuss a little bit with you guys the final exam and the project. Do you guys have any questions so far about the lecture? Let's just start about the lecture. Do you have any questions about the lecture? Okay.
Yes, I have
Okay, yeah, go ahead. Yep.
In our first network, like after when we have specific region, after that we make a one region in which we have the background and foreground, and after that like positive and negative. I don't understand this thing.
The positives and negatives.
Yeah, positive frame update and negative frame update. It's this slide.
Let's go back. Yep. So you're probably talking about these ones, right?
Yeah, long term up. No. Can you go back one more slide?
Yes.
Yes, this one.
So what basically this does is simply you're trying to find let's go back. So we're trying to find is the location of the possible locations of your object. So here, for example, this is the image. This is your video. This is the whole video. This at the starting point, this was the location of your object. Next, it was here. 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 Every time I say next, imagine 1 second passes. This is what I mean with say next, right? 1 second passes. This is the next location of your object. Another second passes. This is the location. This is the location. This is the location. This is the actual locations of your objects, right? This long-term updates or long-term, predictions are what they're doing is they're performed in regular intervals using positive samples collecting for a long period. So you will just be collecting all these positive locations of your object and use them to train your object, right? So you're using your training data to train the model, right? So it's just basic training of basic incorporation of the training data. This is the positive training data. This is your positive samples. These are the positive locations. This is how you are creating them, right? This is how you are creating the positive sample of the training data. How do you create the negative samples, right? Because as we said, we are training a classifier that has a very simple word: positive, negative. That's all it says. And how does it do that? Is by generating a data set of positive samples and generating a data set of negative samples. How do you generate those? From the video. So it's a same video. You have different slides or different frames. Each frame has a different location of the object. All of those can give you different locations like this. So these are the positive locations of the object. Negative locations where he does not exist. So this, like this. So these are locations that for some reason the object did not go to, right? And this helps you basically learn something specific to that object's, how do you say, like walking or motion patterns, right? Does that help a little bit?
Yeah, no, it's okay. I'm just wondering with the positive and long term. It's okay.
exactly. So since the positives are, as we said, they're all on the same place, we're not expecting major change. So this is why they're using this regular long period intervals, so that there is some variation, right? Because in the majority of the cases, you are here on the exact next frame, you're probably like here. So it's exactly on the same place. So it's too much. To make sure that, you know, they do it fast and they do it nice, they just go through a longer period of time, like 1 second, for example, of wait. Any other questions regarding the lectures for today's lecture? Or yeah, maybe even before, on things before this lecture? Okay, seems good. So I just wanted to like ask you guys, are you a bit ready for your project presentations? Are you like, have you made some significant improvements? So I see you are 50-50 in the chat, right? 50% of you want to go like next week exam, and 50 go the week after. Okay, so if that's the case, if you guys are ready for the presentations, then we will have the presentations next week. And we will have the basically final lecture or the final exam on the week after. Seems good?
Yes, 60% want exam next week and then presentation after that.
Okay, seems good.
If you check
right?
the poll, I mean, according to the poll.
Yes, 60-40, right?
Yeah.
Okay, it seems close. It seems too close. But let's see. I think I personally prefer that we do the exam next week. As I said, it's going to be an easy one.
Yes.
Because the presentations there will be like very tightly evaluated. It's going to be good. So you have to, you know, ask her to give you a good grade.
Yeah, that's fine. And like we need to submit some report as well. I mean,
No, you will just do the presentations. After the presentations, you submit the report. Yep.
oh,
But the report will be on GitHub. So it will be a GitHub README report,
oh,
preferably.
okay.
Okay.
Like if we can write like on a paper base, I mean, some 1 or 2 pages reports this way.
Yeah, as you wish. Yeah,
Okay.
absolutely.
Okay, that's cool.
Yeah, for me, the most important thing is that you have a GitHub repo with some good working code, a Colab link that executes that working code, and a beautiful README with lots and lots of pictures. That's something that I need. Yep.
That's fine.
Okay.
Yeah, fine. Thank you very much.
Perfect. Thank you. Remember, for the exam, you will have everything that is imaginable. So from the start, there's no everything's included, basically. Yep.
So exam, like we need to go to the lab, or we can sit in our room and we can do.
I will confirm with Batul if she would be, you know, ready to just receive all of you guys in the same room and just monitor you, but it will be Moodle based, right? So if you, for example, for some reason you cannot attend the lab and you cannot go to the university because you are traveling or something like that, then just send me a message and you can do the exam online.
Yeah, okay. Thank you very much, Professor. Thank you.
Thank you. Good luck, guys. See you next week.
Yeah. See you. Thank you very much.
Goodbye.
Bye-bye.